On the Earth, hydrogen only exists as a diatomic molecule called dihydrogen or in a combined form. This most abundant element accounts for approximately 70% of the mass of the universe. In its combined form, besides water, hydrogen occurs in plant and animal tissues as carbohydrates and many other compounds like hydrocarbons. It is, therefore, the third most abundant element on Earth, constituting 15.4% of its crust and the oceans. Hydrogen with atomic number 1 has 3 isotopes: protium, deuterium, and tritium. It is the only element whose isotopes are named. Protium has no neutrons. Deuterium has 1 neutron, while tritium has 2. Among the 3, protium, with a concentration of 99.98%, is the most abundant. The concentration of deuterium is only 0.0156%, mostly in the form of hydrogen-deuterium molecules. The concentration of tritium is about 1 atom per 10 raised to the power 18 atoms of protium. It is the only hydrogen isotope that is radioactive and emits low-energy beta particles. Because of its atomic number 1, hydrogen is the first element in the periodic table. However, its position in the periodic table is debated because of its resemblance to both alkali metals and halogens, as well as because of its unique behavior. Let us see how hydrogen is similar to alkali metals, yet different from the group at the same time. Its electronic configuration is 1s1. Therefore, like the alkali metals, lithium, sodium, and potassium, hydrogen also has only 1 electron in its outermost shell. Due to this, these elements possess similar electropositive character, allowing them to readily lose an electron to form positive ions. Thus, similar to alkali metals, hydrogen also shows an oxidation state of +1. For example, in hydrochloric acid, hydrogen has an oxidation state of +1, which is similar to that of alkali metals such as sodium and potassium, in sodium chloride and potassium chloride respectively. Like alkali metals, hydrogen acts as a strong reducing agent. For example, it reduces iron 3 oxide to iron, which is similar to the behavior of the alkali metal potassium in its reaction with boron oxide, wherein it reduces boron oxide to boron. Though hydrogen is similar to alkali metals in several aspects, it also exhibits certain properties that are different from alkali metals. For example, the ionization energy of hydrogen is very high as compared to alkali metals. It shows non-metallic behavior, unlike alkali metals. It exists as a diatomic molecule in the form of a gas, whereas alkali metals are solid and exist as monoatomic molecules. Hydrogen mostly forms covalent bonds, whereas alkali metals form ionic bonds. For example, HCl is covalent, whereas NaCl is ionic. Let us now see how hydrogen is similar to halogens, and yet different from the group at the same time. Like halogens, hydrogen has only one electron less than the nearest noble gas configuration. For example, it needs one electron to attain the noble gas configuration of helium. This is similar to halogens, which have an outermost shell configuration of Ns2, Np5 and need just one electron to attain noble gas configuration. The ionization enthalpy of hydrogen, 1312 kilojoules per mole, is very close to that of halogens like chlorine, 1255 kilojoules per mole. The oxidization state of hydrogen, -1, is similar to halogens in some of its compounds. For example, in sodium hydride, hydrogen has an oxidation state of -1, which is the same as that of chlorine in sodium chloride. The molecules of hydrogen and halogens are diatomic. Like halogens, hydrogen is non-metallic in nature and usually exists in gaseous form. In spite of several similarities with halogens, hydrogen also exhibits behavior that makes it different from the halogens. For example, unlike halogens, hydrogen has less tendency to take up an electron to form a hydride ion, whereas halogens form halide ions very easily. In a hydrogen molecule, atoms do not possess any unshared electron pairs, whereas in halogen molecules, every atom has 3 pairs of unshared electrons. The oxides of halogens, such as chlorine oxide, are acidic in nature, whereas hydrogen oxide or H2O is neutral. Because of this unique behavior of hydrogen, it is placed separately in the periodic table. This uniqueness of hydrogen makes it an industrially important element. Now, let's look at the ways to prepare dihydrogen both in the laboratory and industrially. In the laboratory, the most common way of preparing hydrogen is by the reaction of granulated zinc with dilute hydrochloric acid. The setup consists of granulated zinc in a conical flask fitted with a thistle funnel. In this flask, dilute hydrochloric acid is poured drop by drop through the thistle funnel. As dilute hydrochloric acid reacts with the zinc granules, hydrogen gas is released. The gas is collected by the downward displacement of water. Sometimes, the reaction stops midway as the bubbles of hydrogen gas stick to the surface of the zinc granules, preventing its further reaction with the acid. To avoid this, a few crystals of copper sulfate are added to the reaction mixture. Another common method of preparing hydrogen in the laboratory is by the action of metals like zinc and aluminium on strong alkalis like sodium hydroxide and potassium hydroxide. For example, zinc reacts with sodium hydroxide to give sodium zincate and hydrogen. Commercially, hydrogen is prepared by the electrolysis of water using platinum electrodes. Sulfuric acid is used to acidify water, making it a better conductor of electricity. When an electric current is passed through the water, it decomposes into hydrogen and oxygen. Hydrogen gas is liberated at the cathode and oxygen at the anode. The volume of hydrogen formed is double that of oxygen. Another industrial method of dihydrogen preparation is by passing steam over hydrocarbons or red-hot coke at high temperature in the presence of a catalyst, like nickel. The product contains carbon monoxide along with hydrogen. The number of moles of hydrogen and carbon monoxide produced depends on the hydrocarbon. For example, 1 mole of methane produces 1 mole of carbon monoxide and 3 moles of hydrogen. The mixture of hydrogen and carbon monoxide is called water gas. Water gas is further used for the synthesis of methanol and a number of other hydrocarbons, as it produces a lot of heat when burnt. Hence, water gas is also called synthesis gas or syngas. Syngas is also produced from sewage, sawdust, scrap wood, waste paper, etc. When syngas is obtained by the reaction of steam on coal, the process is known as coal gasification. It is difficult to separate dihydrogen from syngas. Therefore, the production of dihydrogen is increased by reacting the syngas with steam in the presence of iron chromate as a catalyst. The reaction produces mixture of carbon dioxide and dihydrogen. The carbon dioxide produced is removed from the mixture by scrubbing with sodium arsenite solution. This reaction is known as water gas shift reaction. Currently, almost 77% of hydrogen required by the industry is obtained from petrochemicals, 18% from coal, 4% from the electrolysis of aqueous solution, and 1% from other sources. Let us first discuss the physical properties of dihydrogen. Dihydrogen is a colorless, odorless, and tasteless gas. It is a non-poisonous gas with a vapor density of 1. Due to this, it is lighter than the air as its vapor density is 14.4. The solubility of hydrogen in water is very low. Under standard conditions, only 2 parts of dihydrogen dissolve in 100 parts of water by volume. Let us now look at the chemical properties of dihydrogen. Dihydrogen gas is chemically inert at room temperature. The chemical behavior of a diatomic molecule is determined by its bond dissociation enthalpy to a large extent. Bond dissociation enthalpy is the energy required to break a chemical bond. It is defined as the amount of energy required to break 1 mole of bonds of a gaseous molecule into fragments in gaseous state at 298 Kelvin and a pressure of 100 kilopascal. In a dihydrogen molecule, the HH bond dissociation enthalpy is very high. This because, as the size of the hydrogen atom is very small, it forms a very strong covalent bond. Thus, it requires an extremely high temperature to dissociate dihydrogen into its hydrogen atoms. For example, at 2000 Kelvin, only 0.081% of dihydrogen dissociates into hydrogen atoms. Only at a high temperature of 5000 Kelvin, we get almost 95.5% dissociation of dihydrogen molecules into its atoms. It is important to note that although a dihydrogen molecule is inert at room temperature, hydrogen atoms are very reactive. This is because they have only one electron in the 1s orbital, and thus they readily combine with almost all the elements to obtain a stable electronic configuration similar to that of helium. A hydrogen atom reacts either by losing one electron to form H-positive ions, or by gaining one electron to form H-negative ions, or by sharing electrons to form single covalent bonds. Let us now look at the reactions of dihydrogen. Dihydrogen gas at high temperatures reacts with highly electropositive metals such as potassium, sodium, and calcium. It combines to form their respective hydrides. In these hydrides, hydrogen exhibits an oxidation state of -1. For example, dihydrogen reacts with sodium to form sodium hydride. Similarly, hydrogen reacts with calcium to form calcium hydride. Dihydrogen burns an oxygen at high temperature in the presence of platinum as a catalyst, forming water and releasing lots of energy. Dihydrogen combines with halogens to form hydrogen halides. For example, it combines with chlorine in the presence of sunlight to form hydrogen chloride. When hydrogen is passed through boiling sulfur, it produces hydrogen sulfide. Dihydrogen reacts with nitrogen at 673 Kelvin and 200 atmospheric pressure in the presence of iron as a catalyst to form ammonia. Dihydrogen reduces metallic oxides of metals that are less reactive, such as copper oxide, lead oxide, and iron 3 oxide, into their respective metals. How does the reaction take place? The metal oxides are strongly heated in a combustion tube. When hydrogen is passed through the tube, the metallic oxides get reduced into their respective metals. Dihydrogen reacts with vegetable oils in the presence of finely divided nickel as a catalyst to give hydrogenated products such as edible fats. Because of its unique properties, like forming non-polluting products and burning in air, dihydrogen gas has many commercial uses. It is used as the rocket fuel because of its high calorific value. An oxyhydrogen blowtorch that is used for cutting and welding purposes uses dihydrogen and pure oxygen. The reaction produces temperature of up to 4000 Kelvin. Dihydrogen is also used in the synthesis of ammonia by Hebbal's process to manufacture nitric acid and nitrogenous fertilizers. Dihydrogen is used in the manufacture of vanaspati. Here, vegetable oils such as soybean are hydrogenated to obtain vanaspati. Commercially, it is used in the preparation of hydrogen chloride as a reducing agent to reduce metal oxides into their respective metals, and also in the manufacture of metal hydrides. You have learned that dihydrogen combines with almost all the elements except noble gases under suitable conditions to form binary compounds called hydrides. These can be represented as EHX or EMHN, where E is the symbol for an element, for example, MgH2 or B2H6. There are 3 types of hydrides depending on the behavior and the nature of the bond formed between the hydrogen atom and the element forming the compound. The types of hydrides are ionic or salt-like hydrides, covalent or molecular hydrides, and metallic or non-stoichiometric hydrides. Let us look at each type in detail. Ionic or salt-like hydrides are binary compounds of hydrogen with S-block elements that are highly electropositive in nature. However, compounds formed with lithium, beryllium, and magnesium exhibit higher covalent character. Ionic hydrides like sodium hydride and calcium hydride are formed by the transfer of electrons from the metal atom to hydrogen atom. This is also why they are called salt-like hydrides. Ionic hydrides are crystalline in solid state. They have high melting and boiling points. Their density is higher than that of the metals from which they are formed. In the molten state, they conduct electricity and, on electrolysis, liberate hydrogen gas at the anode, confirming the presence of negative ions of hydrogen in them. Let's study this using calcium hydride as an example. On passing current through molten calcium hydride, the compound dissociates into calcium 2+ ion and hydride ion. At the anode, each of the two hydride ions combine to liberate dihydrogen gas and 2 electrons. This is an oxidation reaction. At the cathode, each calcium 2+ ion accepts 2 electrons to give calcium. This is a reduction reaction. Ionic hydrides react vigorously with water to liberate dihydrogen gas. For example, sodium hydride reacts with water to give sodium hydroxide and hydrogen gas. Ionic hydrides decompose into highly inflammable dihydrogen and undergo combustion when strongly heated in air. For example, calcium hydride, when heated at 675 to 775 Kelvin, decomposes into calcium and dihydrogen. Unlike other ionic hydrides, lithium hydride is unreactive at moderate temperature with oxygen and chlorine gas, and is used in the synthesis of other useful hydrides such as lithium aluminium hydride and lithium boron hydride. The reaction that takes place is lithium hydride reacts with aluminium chloride to give lithium aluminium hydride and lithium chloride. Lithium aluminium hydride is a powerful reducing agent and used extensively in organic chemistry. Lithium hydride also reacts with boron hydride to give lithium boron hydride. The second type of hydrides are covalent or molecular hydrides. Covalent or molecular hydrides are binary compounds of hydrogen with more electronegative elements, such as p-block elements. They are bonded by covalent bonds. For example, CH4, NH3, H2O, and HF. Covalent hydrides are further classified into 3 types, depending on the number of electrons and bonds present in their Lewis structures. The 3 different types are electron-deficient hydrides, electron-precise hydrides, and electron-rich hydrides. As the name suggests, electron-deficient hydrides do not have the required number of electrons to write their conventional Lewis structure. In other words, they do not have complete octets. The hydrides of group 13 form electron-deficient compounds. For example, in borane BH3, boron has 3 electrons in its outermost shell and forms 3 covalent bonds with 3 hydrogen atoms, resulting in an incomplete octet with only 6 electrons. Another example is aluminium hydride, or alane, AlH3. Due to their incomplete octets, these hydrides generally exist in polymeric form. For example, BH3 exists as diborane B2H6. They act as Lewis acids, that is, electron acceptors, as they are electron deficient. Electron-precise hydrides have the required number of electrons to write their Lewis structure. In other words, they have complete octet and are formed by the elements of group 14. For example, in methane CH4 and silane SiH4, both carbon and silicon have 4 electrons in their outermost shells and form 4 covalent bonds with 4 hydrogen atoms to complete their octet. Electron-rich hydrides have excess electrons, which are present as lone pairs. The elements of group 15, 16, and 17 form such hydrides. For example, NH3 has 1 lone pair on nitrogen. H2O has 2 lone pairs on oxygen, and HCl has 3 lone pairs of electrons on chlorine. Due to the presence of excess lone pairs, these hydrides behave as Lewis bases, which are electron donors. These hydrides also form hydrogen bonds between molecules due to the high electronegativity of nitrogen and oxygen. Electron-rich hydrides are poor conductors of electricity and are soluble in organic solvents. The third type of hydrides are metallic hydrides. They are binary compounds of hydrogen with D and F block elements. However, except for chromium from group 6, the metals of group 6, 7, 8 and 9 do not form hydrides. The inability of these metals to form hydrides is called the hydride gap of D block. Metallic hydrides are deficient in hydrogen and are almost always non-stoichiometric. For example, LaH2.87, YbH2.55 and TiH1.5 to 1.8. The composition of these hydrides does not correspond to simple whole number ratio and also varies with change in temperature and pressure. And hence, these hydrides are also called non-stoichiometric hydrides. Earlier, it was thought that hydrogen, being very small in size, occupied interstices in the metal lattice in these hydrides, and hence they were named interstitial hydrides. However, recent studies have shown that except for the hydrides of nickel, palladium, cerium, and actinium, the other hydrides of this type have lattices different from the parent metal. The property of absorption of hydrogen on transition metals is widely used in catalytic reduction and hydrogenation reaction in the preparation of a large number of compounds. Metals like palladium and platinum can accommodate a very large volume of hydrogen and can be used as media for its storage. Metallic hydrides are good conductors of heat and electricity and are harder than the parent metal. We all know that water is essential for the survival of all forms of life. It forms a major part of all living organisms. 60% of the human body is made up of water. And in some plants, this quantum goes up to 90%. Water covers 71% of the Earth's surface. However, the distribution of water over the Earth's surface is not uniform. Oceans contain 97.33% of water on the Earth's surface. Only 2% of water on the Earth's surface is in the form of polar ice and glaciers. The remaining water, less than 1%, is present in lakes, rivers, in the atmosphere, and as underground water. Let us now look at some physical properties of water. Water is a tasteless and odorless liquid at standard temperature and pressure. It freezes into ice at 273 Kelvin. Its boiling point is 373 Kelvin and has a density of 1 gram per cubic centimeter at 298 Kelvin. Water has strong hydrogen bonding in its molecules and, therefore, exists as associated molecules. Due to the presence of extensive hydrogen bonding in its molecules, water has a high freezing point, a high boiling point, a high heat of vaporization, and a high heat of fusion in comparison to hydrides formed from other group 16 elements, like H2S and H2SE. In comparison to other liquids, water has high thermal conductivity, surface tension, dipole moment, and dielectric constant respectively. And also, it has highest specific heat. These properties allow water to play a key role in the biosphere. Its high heat of vaporization and high heat capacities are responsible for the moderation of the climate and the body temperature of all living beings. Water is an excellent solvent for the transportation of ions and molecules required for animal metabolism. Due to hydrogen bonding with polar molecules, even covalent compounds such as alcohol, and carbohydrates dissolve in water. The shape of water molecule is bent or V-shape with a bond angle of 104.5 degrees and OH bond length of 95.7 picometers. In water molecule, as the oxygen atom has a higher electronegativity than hydrogen atom, it carries a partial negative charge, whereas the hydrogen atom carries slightly positive charge. As a result, water is a polar covalent molecule. In the liquid phase, water molecules are associated by hydrogen bonds. The crystalline form of water is ice. At normal atmospheric pressure, ice crystallizes in hexagonal form. The density of ice is 0.9167 gram per centimeter cube at 273 Kelvin, whereas water has a density of 0.9998 gram per centimeter cube at the same temperature. In winter, the frozen ice on the surface of the lakes provides thermal insulation and is important for the survival of aquatic life. Ice has highly ordered three-dimensional hydrogen-bonded structure, in which every oxygen atom is surrounded tetrahedrally by four other oxygen atoms at a distance of 276 picometers. Hydrogen bonding gives ice a rather open crystal lattice structure with wide spaces between the molecules. These vacant spaces can hold some other molecules of appropriate size interstitially. Chemically, water reacts with large number of substances. Let us look at some of these reactions. Amphoteric nature. Water is amphoteric in nature, which means that it can act as an acid as well as a base. According to the Lowry-Bronsted concept, water can act as an acid by losing a proton and as a base by accepting a proton. For example, in the reaction with ammonia, water acts as an acid by giving H plus ion and forming NH4 plus ion. In the reactions with hydrogen chloride and hydrogen sulfide, water behaves as a base by accepting H plus ions and forming H3O plus ions. Water also undergoes autoprotolysis or self-ionization, in which one molecule of water acts as acid 1 and another molecule as base 2 to give a molecule of acid 2 and base 1. These are also known as conjugate acid and conjugate base. Redox reactions involving water. Water can easily be reduced into hydrogen by highly electropositive metals. For example, sodium metal reacts with water to give sodium hydroxide and hydrogen. Therefore, it is a great source of hydrogen. Water is oxidized to oxygen during photosynthesis. The reaction that takes place is 6 molecules of carbon dioxide react with 12 molecules of water to give 1 molecule of glucose, 6 molecules of water and 6 molecules of oxygen. It also reacts with fluorine gas to give oxygen and ozone. Hydrolysis reactions. Water is a strong solvent and dissolves many ionic compounds. However, due to its high dielectric constant, it has very strong hydrating tendency and can easily hydrolyze many ionic and covalent compounds. Water hydrolyzes the oxides and halides of nonmetals to their respective acids. For example, it hydrolyzes phosphorus pentoxide to give orthophosphoric acid. It also hydrolyzes silicon tetrachloride to hydrochloric acid and silicon dioxide. Water also hydrolyzes the carbides, hydrides and nitrides of some metals. For example, it hydrolyzes both calcium carbide and aluminium nitride to give ethyne and ammonia respectively. The reactions that takes place are: calcium carbide reacts with water to give calcium hydroxide and ethyne. Water reacts with aluminium nitride to give aluminium hydroxide and ammonia. Hydrate formation. Many salts can be crystallized as hydrated salts from their aqueous solutions. There are three types of hydrates. The first type of hydrate is coordinated water. For example, in CrH2O6 3 plus 3Cl minus, water molecules are coordinated to metal ions in a complex. The second type of hydrates is interstitial water. For example, in BaCl2 2H2O, water molecules occupy interstitial sites in the crystal lattice. In the third type of hydrates, water molecules are hydrogen bonded to certain oxygen-containing anions. For example, in CuSO4 5H2O, one water molecule is hydrogen bonded to sulfate ion, and the other four molecules are coordinated to give CuH2O4 2- plus SO4 2H2O. Water is classified as soft and hard depending on the type of dissolved salts and behavior with soap. Soft water produces lather easily with soap and contains no calcium or magnesium ions. A good example of soft water is rainwater. Hard water, on the other hand, does not produce lather with soap easily and cannot be used for laundry. For example, river, sea, and sometimes even well water. The hardness of water is due to the dissolved salts, like bicarbonates, chlorides and sulfates of calcium and magnesium ions. When rainwater makes its way through the ground, it dissolves the salts of calcium and magnesium and turns hard. Let's see why hard water cannot be used for laundry. Hard water contains calcium and magnesium cations, which reacts with soap to form scum or precipitate of calcium and magnesium salts or fatty acids. Laundry soap contains sodium stearate. When sodium stearate reacts with the calcium and magnesium salts, it forms calcium and magnesium stearate precipitate. Until all the calcium and magnesium ions are precipitated, lather is not produced. This is why hard water is unsuitable for laundry. Hard water is also harmful for the boilers because of the deposition of salts in the form of scales, which reduces the working efficiency of the boilers. Hardness of water can be classified as temporary hardness and permanent hardness. Temporary hardness of water is due to the presence of soluble calcium and magnesium hydrogen carbonates, respectively. There are two common methods to remove temporary hardness. The first method is boiling. Hard water is taken in a large boiler. During boiling, the soluble magnesium hydrogen carbonate is converted into insoluble magnesium carbonate, while calcium hydrogen carbonate changes to insoluble calcium carbonate. The precipitates of magnesium carbonate and calcium carbonate are removed by filtration, leaving soft water as the filtrate. The second method to remove temporary hardness is known as Clark's method. In this method, a calculated amount of lime is added to hard water. It precipitates out calcium carbonate and magnesium hydroxide, which can be filtered off. Permanent hardness is due to the presence of salts of magnesium and calcium in the form of chlorides and sulfates. Permanent hardness cannot be removed by boiling. It is removed by other methods, which include treatment with washing soda, Calgin's method, ion exchange method, synthetic resins method. Let us look at each of these methods in detail. Treatment with washing soda or sodium carbonate. A calculated amount of washing soda is added to hard water. Washing soda reacts with the soluble chlorides and sulfates of calcium and magnesium in hard water to form insoluble carbonates. The second method of removing permanent hardness is Calgin's method. In this method, calcium and magnesium ions are not removed from the water, but are rendered ineffective by the addition of sodium hexametaphosphate, commercially called Calgin. Calcium and magnesium ions react with Calgin to form a soluble complex. The complex anion keeps the magnesium and calcium ions in solution, not allowing them to react with soap. In ion exchange method, also called the zeolite or permutate process, hydrated sodium aluminium silicate or zeolite, when added to hard water, exchanges cations such as magnesium and calcium ions for sodium ions. For simplicity, sodium aluminium silicate NaAlSiO4 is written as NaZ. Once all the sodium in the zeolite is used up, it is regenerated for further use by treating with an aqueous sodium chloride solution. The fourth method of removing permanent hardness is the synthetic resins method. In this method, synthetic cation exchanges are used. This method is more efficient than the zeolite method. Cation exchange resins contain larger organic molecules with groups such as SO3H or COOH that are water insoluble. They exchange their H+ ions with the cations in hard water. Anion exchange resins contain organic molecules with groups such as NH3OH that exchange their OH- ions with the anions present in hard water. Pure demineralized or deionized water, free from all soluble mineral salts, is obtained by passing hard water successively through a cation exchange in the H+ form and an anion exchange resin in the OH- form. In the cation exchange process, the H+ ions in RCOO-H+ are exchanged with sodium, calcium and magnesium ions present in the hard water. The reaction that takes place is RCOOH in solid state plus N2+ in aqueous solution gives MrCOO taken twice plus 2H plus ions in aqueous solution, where M plus 2 is a calcium or magnesium cation. Since this reaction releases H plus ions, it makes water acidic. In the anion exchange process, RnH2 in water gives RnH3 plus OH minus. The OH minus ion in RnH3 plus OH minus gets exchanged with chloride, bicarbonate and sulfate anions present in the water. The reaction that takes place in RnH3 plus OH minus reacts with X minus to give RnH3 plus X minus and OH minus ions, if X is chloride ion. The released OH minus ions neutralize H plus ions. Once the cation and anion exchange resin beds are exhausted, they are regenerated by treatment with dilute acid and alkali solutions respectively. Hydrogen peroxide is a very pale blue liquid and appears colorless in a dilute solution. It is naturally produced in organisms as a byproduct of oxygen metabolism. It is a strong oxidizing agent. In fact, it is such a highly reactive oxygen species that all living aerobes form peroxide enzymes to decompose the hydrogen peroxide formed within the body into water and oxygen harmlessly and catalytically. Structurally, the hydrogen peroxide molecule is non-planar. It has an open book structure. The presence of lone pairs of electrons on the oxygen atoms and the hydrogen bonding gives the molecule a different structure in gaseous and solid phases. In gaseous state, hydrogen peroxide has a dihedral angle of 111.5 degrees, whereas in solid state, at a temperature of 110 Kelvin, it has a dihedral angle of 90.2 degrees. This affects its physical properties. It has a melting point of 272.4 Kelvin, a boiling point of 432 Kelvin, a vapor pressure of 1.9 millimeters Hg, a solid density of 1.64 gram per cubic centimeter, and a liquid density of 1.44 gram per cubic centimeter. Its viscosity is slightly higher than water at 1.25 centipoise. Its dielectric constant at 298 Kelvin is 70.7 Coulomb square per Newton meter square. And electrical conductivity is 5.1 into 10 raised to minus 8 ohm per centimeter. Chemically, it acts as an oxidizing as well as a reducing agent in both acidic and basic media. So, let's now look at the reactions that take place in acidic media. In an acidic medium, as an oxidizing agent, hydrogen peroxide reacts with ferrous ions to form ferric ions. As a reducing agent, it reacts with sodium hypochlorite and yields water, sodium chloride, salt, and oxygen. This reaction is also used in laboratories to prepare oxygen. Now, let's look at the reactions that take place in basic media. Here, as an oxidizing agent, hydrogen peroxide reacts with ferrous ions to form ferric ions. As a reducing agent, It reacts with iodine to form iodide ions along with water and oxygen. For example, if potassium hydroxide is taken as the base, then potassium iodide salt is formed. On exposure to light, hydrogen peroxide undergoes slow decomposition to form water and oxygen. Metals and traces of alkaline compounds hasten this reaction. And this is why hydrogen peroxide is always stored in plastic bottles and kept in the dark. In recent years, the demand for hydrogen peroxide has increased as it has found widespread use in pollution control treatment of domestic and commercial effluents. In laboratories, hydrogen peroxide is prepared from barium peroxide or acidified sulfate solution. To obtain hydrogen peroxide from barium peroxide, first acidify barium peroxide with sulfuric acid. Barium sulfate is precipitated and an aqueous solution of hydrogen peroxide is produced. The excess water is then removed by evaporating the solution under reduced pressure. This will give us hydrogen peroxide. You can also obtain hydrogen peroxide from 50% sulfuric acid solution. The solution subjected to electrolytic oxidation to yield peroxydisulfuric acid. The peroxydisulfuric acid formed undergoes hydrolysis to form hydrogen peroxide. During electrolysis, hydrogen peroxide is formed at the anode. Peroxydisulfuric acid is formed as a byproduct at the anode. Hydrogen gas is evolved at the cathode. Commercially, hydrogen peroxide is prepared by auto-oxidation of 2-ethyl anthraquinol. First, air is passed through 2-ethyl anthraquinol to yield 2-ethyl anthraquinone and hydrogen peroxide. The product, 2-ethyl anthraquinone, is then reduced. For this, hydrogen under a pressure of 1 to 3 atmospheres at 4 degrees centigrade is passed over 2-ethyl anthraquinone. This gives back 2-ethyl anthraquinol, the reactant. This reaction gives a dilute solution of hydrogen peroxide. It is then extracted with water and the solution of the required concentration is prepared. It is customary to indicate the strength of hydrogen peroxide solution in terms of the volume of oxygen at NTP that 1 volume of hydrogen peroxide gives on heating. When the grade of H2O2 in volumes is given, its percentage strength can be calculated. We come across many uses of hydrogen peroxide every day. For example, as a mild disinfectant, as a cleanser, as a bleaching agent in the textile, paper pulp, leather, oils and fats industries, as a pollution control agent in the treatment of domestic and industrial effluents, oxidation of cyanides, restoration of aerobic conditions to sewage wastes, and so on. Thus, we see that hydrogen peroxide is an important compound. Today, we mostly use fossil fuel to power our growth. The demand for fuel is so huge that it is believed that by the middle of the 21st century, the world will run out of fossil fuel. For this reason, the race is on to develop alternative energy sources. One of the major alternative sources in use today is nuclear energy. However, it can only be used to obtain electrical energy, but only 20% of the total energy required constitutes electrical energy. So, for the remaining 80% energy requirement, scientists are still searching for a viable energy source. One of the most promising alternatives they are currently studying is the use of hydrogen as a fuel. Hydrogen has many advantages over all other options. For example, it is abundantly available. Its combustion product being water, it is pollution-free. It yields almost double the energy provided by jet fuels. For example, liquid hydrogen is used as a rocket fuel. This fuel has water as its product instead of harmful carbon dioxide, sulfur dioxide, and other hydrocarbons. However, it is not yet used on a large-scale basis because pure hydrogen gas is not readily available. Hydrogen gas is highly flammable and explosive to handle. Storage and transport of hydrogen gas is very expensive. The cost of production of hydrogen is very high at this point of time. Although some cars using hydrogen fuel are already in the American and European markets, commercial use of hydrogen as one of the most eco-friendly energy alternatives has still a long way to go.